Hello world, here's Jorge, and let's continue learning about object detection in PyTorch. In the last video, we visualized the entire set of mandatory training road signs contained in the data set that we were dealing with. Okay. Now, before we go actually and move on to the HOG feature extractor, we are going to visualize the other object classes too. Okay, so let's have a look. Now let's say we want to visualize the prohibitory. Okay, all right, let's see how it looks. Great. It looks like, at least at the bare eye, it looks like we have more prohibitory signs than mandatory, but we can actually check that, of course. And how? Well, remember that we had a subkey called boxes, and we said that we had 4D vectors there that were associated to individual cropped images. So if we know how many boxes of those we have how many, we're gonna know how many images we are actually seeing right now. So let's do that. So how could we verify that? Well, we could call the actual subkey boxes. Yeah, the training data set, remember. And let's check the shape, because the shape is going to contain as the first element the number of boxes. Okay, so these are the images, the number of images of prohibitory style that we have in the set. Okay, all right, but now actually let's check the mean road sign in the set. And why is that useful? Well, if we check the mean road sign, we are going to understand what is the most repeated sign, if there's any. Okay, because we're going to be able to visualize what are the most common features out of the whole set. Okay, in this case of prohibitory signs. Yeah. So let's code that out, and to do that we are going to use the imsc function. All right. So what subkey should we call here? Well, we're going to call the box patches, right? Because remember, the box patches had as a dimension NCHW, that is number of cropped images, color channels, height, and width. All right. So what we want to do is actually average on the first dimension of that vector, that is in the number of cropped images. Okay. So let's call that. So we have train and the subkey box patches. All right. And we are going to take the mean of the first dimension. All right. And remember that IMSC actually takes vectors of the shape, basically color channel, height, and width. Okay, so 3D-dimensional vector. Whilst here we have a 4D vector, because we also have the cropped images. But what happens is that when we average over these first dimension, we're going to collapse it. So the resulting shape of the vector is going to be 3D, two-dimensional. Okay. Well, anyways, let's run this. Okay, interesting. So it looks like we have a shape that is clear. So we have most present in the data set prohibitory signs of speed limit, and more precisely speed limit of 2 digits, because if you check the original, we have also of 100 here, and 120 and so on. But most common out of all, not only speed limit but others, the most common is actually 2-digit speed limit. And more precisely, this looks like we have a combination of 30 here, I would say, and also here we have kind of a 5. So it looks like 30 and 50 are the most common out of this set. Okay, great. So now let's actually perform the same analysis for the mandatory. Same. You see, we have 87 mandatory signs in the training data set. Okay, great. But so here we observe a clear dominant sign within the training data set for mandatory signs, that is bottom right. So bottom right looks like is the dominant sign in this training set. Very interesting. And now let's check the last. Let's check danger. Okay, then we have 127. Oh, very interesting. You can see there is no clear pattern here. I mean, I kind of see the shape of a person, so you could argue that maybe this one is the most common, but it's not clear, to be honest. It's not really defined, right? So I would say there's no clear dominance in this case, in this danger road sign set. Okay, very interesting. But yeah, just for fun, remember that we had the all option. So what is going to happen if we run it for all? I'm just curious. Let's see. So you see, for all we have 691, as we saw in the first video, and see what's going to happen with the mean actually. Oh wow. Okay. All right, it looks like a mix, right? I'm surprised that we don't have the mandatory. I guess it's because it's the last common of all, right? Compared to, well, we have 691, and maybe the mandatory is the one with less weight, you could say. And it looks like definitely the dominant is the prohibitory. The danger, you can see the triangle, you can see it there, but definitely would say that out of all data set, the prohibitory is the type of road sign that is most common. Okay, very, very interesting. But yeah, let's continue now, and let's move actually to the histogram of oriented gradients. Okay, great. So essentially, something important to notice here is the following. So we're dealing with object detectors, and these object detectors normally work on top of a layer. With low-level features. What do I mean by that? So essentially, that means that low-level features essentially are used to give to the detector clues to help it learn to recognize target classes. Okay, we are going to use a CNN to extract our features, but we are not going to do it the usual way, that being just let the CNN learn by itself the features. Okay, no, we're not going to do it like that. We're going to take a shortcut by basically designing a network or a model that computes the actual features. Okay, so it's going to compute the features, so no extraction, so no, say, you could call it, automatic extraction. It's going to happen, but rather we're going to code it. We're going to code that feature extraction, okay, by defining a model, which is what's known as HOG model. Yeah, we're going to call it HOGNet. Okay. This model is going to take as an input a grayscale or an RGB image, okay, which is going to be represented by a PyTorch tensor with the actual size and C, H, and W. Okay, right. Fantastic. So now let's move on and let's try to understand some key parameters for our model. But first, what I did here was to write snippet to actually be able to format equations, to be able to format equations in this notebook, okay, by calling this mathjax package, okay. All right, so now let's move on and let's talk about these two key parameters, okay. It's going to be cell size and number of orientations. All right, so what do I mean by these two? Okay, so we need to understand that the HOG algorithm divides the original image, the input image, into equally sized cells. Okay, so the cell size is going to simply determine this size in pixels of such cells. All right. So essentially, for each cell, then we're going to compute a histogram. We're going to compute this HOG parameter. Okay. All right. So we need to understand that smaller cells are going to capture finer details, while larger cells are going to capture more global, coarser features. All right. So essentially, in short, you could say that this cell size determines the spatial resolution of the features. Okay. That's regarding these cell size. What about the number of orientations? This number of orientations is going to determine how many bins are used in the histogram for each cell. Okay, so in other words, what we're going to have is we're going to define an angular range where our gradient is going to be located. All right, and just as an example, we're going to set this cell size is equal to 8 and number of orientations is equal to 9. So for instance, what does it mean that the number of orientations is equal to 9? Well, we need to understand that the range of angles in general is given by the following. It's given by is between 0 and 360, okay, degrees. Okay. So if we set the number of orientations equal to 9, we need to divide the whole range by 9. So in this case, it would be 360 divided by 9, it's going to be 40. So we're going to have from 0 to 40, that's going to be one range. One bin, better say one bin. Then from 40 to 80, second bin. From 80 to 120, another bin, and so on until 360, okay? That's clear now, but now let's actually take a practical example, or better say just an example to further understand how these two are going to be key in our HOG algorithm, okay? And for that, let's go to the CNN website, the CNN explainer, which is very useful to understand in a, say, practical and general manner how convolutional neural networks actually function, okay? But now let's focus on the input, okay? So as you can see, we have an input image of 64,3. By the way, remember that we always work with color channels first because we are working with PyTorch, okay? But when we need to actually plot images, remember when we use Matplotlib, we need to actually permute the order and put the image, say the color image dimension last, okay? But yeah, that's an aside. Let's continue now understanding how are we going to apply these two variables, all right? So first of all, we have these cell size. The cell size that we set, we're going to set equal to 8, okay? This means that we are going to subdivide our original cell, which is originally 64 by 64 pixels, into a number of 8 by 8 cells, 8 by 8 pixel cells, okay? And of course, we're gonna have 64 of those, yeah, because we're gonna have 64 divided by 8 is going to be 8. Same for the width, and we're gonna have 8 by 8, but that is times basically 8, so we're gonna have 64 again, yeah? So we basically we're gonna have 8 by 8 cells, and we're gonna have 64 of them, all right? That is the message. And the key to understand here is that we need to compute one histogram per each of these 64 cells, okay? So we're gonna resulting in 64 histograms per channel, because remember, here we're just taking into account one channel, because as we'll see later, we need to then multiply the final result by 3 if we want the total number of features, okay? But we'll go to that. Let's just now focus on having just one channel, okay? And more precisely, let's just focus on having just these 8 by 8 cells. Let's just take one of these 64. Let's just take one of these 64 8 by 8 cells. And let's understand how are we going to compute the histogram vector for one of those. And to simplify this further, I have drawn here just 4 pixels out of the 16 of these 8 by 8, because remember, now we're just focusing on one subcell of 8 by 8, yeah, and there we have 16 pixels, but let's just focus on 4, okay? So for each pixel, we're gonna have a pair of values. What kind of pair of values? Well, we're gonna have these, this degree, okay, which essentially represents the gradient direction, okay, the gradient direction. The range, so it's going to determine, it's going to tell us in what range is our gradient located at, okay? That's one thing. Then we have the other value, which represents the gradient magnitude, okay? This represents the gradient magnitude. So for each pixel, we're going to have this kind of pair, okay, associated to it. Great. So what is next? So what we need to understand is that we need to place the gradient values, the gradient magnitudes, in specific bins, okay? So how many slots are going to have, or are we going to have in our feature vector? Well, we're going to have 9, because of course that is the number of orientations that we set, okay? So for instance, in the first one, the first slot corresponds to the range of 0 and 40, okay? And what is the only value? So in this case, we just have one value that is in this range, okay? That is 5, this 5 gradient magnitude. So we write the gradient magnitude. So these features actually are simply these gradient magnitudes, okay? And one interesting question would be, okay, what happens if we have several gradient magnitudes within the same gradient direction? their gradient angle. Should we add them up? The answer is yes. We need to add the gradient magnitudes if they are located in the same gradient direction range. All right, fantastic. So as you can see, what happens here is that, okay, 0, 40, we just have one. 40, 80, we just have these three. 80, 120, we have these two. And see, check that we don't have any value for 120, 160, okay, and nor the following. So we place 0 until we reach, you see, we have this 4 associated to the range 320, 360. So we place it where it's located, the order that corresponds to the last slot. Great. So that is how you calculate. Okay, and remember, this is totally simplified for even for our 8x8 cell, because it should be there should be 16 pixels. We just are seeing 4 here. But anyways, we understand now how to construct the histogram vector. Okay, and the question is now, okay, how do we generalize this? So in the sense that now remember that we said that we had 9 features per feature vector. Okay, and remember that we have one of these vectors per cell, and we have 64 cells. Okay, so this means that if we ask the question, okay, how many features does your image have? The answer is basically to multiply 9 by 64 images. 64 cells. Okay, so in that case, we will have 576 total features. Okay, for our entire image. But remember, we stressed that we were dealing with just one channel. So what if I say, okay, I want you to determine the total amount of features for the 3 channels? So simply, what you would need to do is to just multiply 3 times 576, so that you would have 1728 HOG features, the total amount for the, say, for your image with 3 color channels, red, green, and blue. Okay, but great. That's actually all that I wanted to talk about for this video. And next we'll continue actually learning more about HOG and how to construct it. Next, actually, the next step will be to talk about the gradient filter. So how are we going to hard code the weights of our kernel? Okay, but yeah, we'll see that next. So again, thanks for your attention, and I am willing to see you very soon.